So in this section, we're going to be focusing on all of the different things that the second derivative can tell us. Last time it was what can the first derivative tell us. So the very first thing that we can talk about with the second derivative is concavity. So concavity is defined as a section of the graph where f prime is increasing on an interval for concave upward and concave downward when f prime is decreasing on an interval. So if you want to think about this from a visual perspective, imagine you're standing out in the rain and you're trying to keep your head dry. You could either hold a bowl over your head to catch the rain, so that would be like concave upward, or you could hold an umbrella over your head to deflect the rain, so that would be like concave downward. So up like up like a bowl, down like an umbrella. So one thing that's important to note about the distinction between the two, it says f prime is increasing. So if you look at the tangent lines from left to right, you can see that they're getting more steep. The slope is increasing. You can also see that the graph is actually lying on top or above all of its tangent lines. On the concave downward section, you can see that the slope is decreasing. It's getting more and more negative as you go from left to right. And you can also see that the graph of f is lying below its tangent line. So all those blue tangent lines are above the graph. So that's kind of the geometric difference between the two. And of course, within the same graph, you can have two different concavities. So you may end up with a shape that looks something like this. And you'll notice that there's some point in the middle where it changes from concave downward on the left to concave upward on the right. So we're going to be talking about where that happens and how to figure out what the different intervals are. So the test for concavity is basically this. We're looking for where f prime is increasing or decreasing. So we can treat f prime as a function and find the intervals on which it's increasing or decreasing by finding its derivative and setting up intervals and test points and going through that same process. So basically, we're going to be finding the second derivative, setting it equal to 0. Those are going to be the possible boundary points for this, and then we're going to plug test points into the second derivative. So let's look at an example. I'm going to find, just like before, I'm going to find f double prime of x and use it to find the critical values or critical points of f prime of x. So I'm going to start by finding the first derivative first, which in this case would be 6x minus 3x squared, and then I'm going to find the second derivative, which would be 6 minus 6x, and that exists everywhere, and it's equal to 0 when 6 equals 6x or x equals 1. And then my next step is going to be to set up intervals and choose test points. And then my final step is going to be to evaluate f double prime of x at each test point. So let's go through that process. So my intervals, we're going to take our whole domain, which is from negative infinity to infinity, negative infinity to infinity, and we're going to split it at 1. So I'm going to pick test points. Let's do 0 and 2. And I'm going to plug into f double prime of x. So that'll be 6 minus 6 times 0, which is 6, so that's greater than 0. And 6 minus 6 times 2 is negative 6, so that's less than 0. So our concavity is that this is concave upward, and this is concave downward. So we are concave upward from negative infinity to 1, and we are concave downward from 1 to infinity. Now another part of this is that point where it changes from concave upward to concave downward or from downward to upward. And that's what we call a point of inflection. So if you let f be a function that's continuous on an open interval and c be a point in the interval, if the graph of f has a tangent line at the point CF of C, then this point is a point of inflection of the graph of f when the concavity of f changes from upward to downward or downward to upward at that point. So think about this statement. If the graph of f has a tangent line at the point CF of C. So in order for this to be a point of inflection, you must have f defined at the point. So f actually has a point at CF of C. And you also have to have the derivative either exists and gives you a value, or it doesn't exist and you have this vertical tangent line type situation. So either one of those would work. But also it has to change from one point to another. So let's do some more examples. It says determine the open intervals on which the graph of x to the fourth minus 4x cubed is concave upward or downward, and find any points of inflection. So we're going to start off by finding the derivative, which would be 4x cubed minus 12x squared, and we're going to find the second derivative, which would be 12x squared minus 24x. So I'm going to set that equal to 0 because it does exist everywhere. Factor out a 12x and I get x minus 2. So I get the points 0 and 2. Okay, so I set up intervals, and we're going to go from negative infinity to 0, and 0 to 2, and 2 to infinity. So I'll pick my test numbers, pick whatever you like that's in the interval, so I'll do negative 1, 1, and 3, just because that's what I like. F double prime of x, if I plug in the negative 1 into my calculator, and again I'm plugging it into f double prime, so that's 12x squared minus 24x, I get 36, which is positive. If I plug in the 1, I get negative 12, which is negative, and if I plug in the 3, I get 36, which is positive. So my concavity here is concave upward. Here I would have concave downward because it's negative. And here I would have concave upward. And since it's changing from upward to downward here, this is a point of inflection, or an inflection point. This is also a point of inflection. So we have a point of inflection at 0 something and 2 something, and if you want to find out what those y values are, you go back to the original function. So that's 0, 0, and f of 2 would be 2 to the 4th minus 4 times 2 cubed, which ends up giving me negative 16. So these are the intervals on which it's concave upward or downward. That'd be negative infinity to 0, and 2 to infinity for upward, 0 to 2 for downward, and then your points of inflection here.